Okay, welcome to Physics 113 lab. Do this remotely. It's going to be a little different for both of us. This week we're going to be looking at equilibrium of forces, but we're going to be applying it to rotation. Okay, so it's equilibrium of forces. We've looked at this before in the past when we used a force table and we tried to balance forces out on that table and we looked at the force balances. We're going to do a similar thing today, except for there's a new twist to it, and that is we need to consider rotation. All right, so when you talk about rotational motion, the analogous thing that happens between linear and rotational motion is you'll be able to compare the two in lecture. You'll see things such as theta compared to r. You'll see velocity, your linear velocity compared to your angular velocity. You'll have angular acceleration that's analogous to the linear acceleration. And so you'll see patterns develop there. Another pattern is going to be force and its partner in rotation, which is torque. Okay? So most of what you'll find is you typically will take your linear idea and multiply it by a distance, a placement, wherever the force is applied or whatever the length is or the radius of something. So you'll see this kind of pattern emerge in linear and rotational motion. So if I'm looking at torque, R cross F is the torque. If you take the torque being a vector, R being a vector, and the force being a vector. So you would take the cross product of the R, which would be the radius vector from wherever your point of rotation, your origin of rotation would be out to the place which the force is applied. That would be R, multiplied by whatever the force actually is and the direction for the force. So the cross product mathematically takes care of one of these issues for us that we're going to talk about in just a moment. So I'm going to use something we use every day as an illustration, and that would be the door. Since you're far away from campus most likely, then you get a chance to remind you how much you miss physics lab. So here's our door. And if I want to open this door, then I need it to rotate. Okay? About which point I rotate is going to be the hinge. So this will be my point of rotation here, my axis of rotation. Now, I'm going to apply a force somewhere at a distance away from that R. I'm going to apply that force, say where I have my hand about at this point here on the other side. I'm going to apply that force and be able to open this door. Now, keep in mind, though, that the only part of the force, remember force is a vector, so if I'm applying a force to the door, I could be applying a force like this, or like that, or like this, perpendicular to it, or I could even apply a force like this. I could pull on the door, or I could push the door. But if I do that, if I push the door right directly at, if my force is pointed directly at the hinge over here, or if I pull completely parallel to the door, away from the hinge, the only thing I could ever succeed in doing would be potentially pushing it through the wall or pulling it off the wall in a linear fashion, but I'll never cause a rotation. So the rotation part is going to come when you apply a force that is at any angle relative to this R. Okay? So if you look in the equations in the text, you'll see that they have FR sine of theta, theta being the angle between the force and the radius vector. All right? So sometimes referred to as a moment arm. So in other words, the only part of the force that matters to make this door open is the perpendicular component, and that's what the cross product takes care of for us in the vector algebra. So, or we can do it directly here by doing the FR cosine of theta that they have listed in the text, so that we only get that perpendicular component. So we'll come back to that when we start to make measurements for the lab. So in other words, if I go to open this door, if I put a pressure in this direction, then some of that force would be pushing it into the wall, which is not really helping. But some of that force, the perpendicular component, would be causing it to rotate. Okay? So now we have that out of the way. We'll walk over to the lab table and we'll begin to set up the experiment and take data. Okay, for the experiment, we are going to have a meter stick, and this is going to be the object that we apply the forces to. So we're going to have the meter stick here. We're going to place a clip on here to run the masses. So we're going to have mass over a pulley pulling down. So in other words, there will be a force in this direction. There will be a force in this direction. There will also be two hanging masses that we're going to place hanging off of this here. So there will be two forces in the downward direction. But there's one other force that we must not forget, and that is the weight of the meter stick. And we're going to make one little assumption here. We're going to assume that the center of mass is at 50 centimeters. If we slide along here, this one is pretty close. It's within maybe like probably about a little less than half a centimeter away from 50, balancing it out this way, so not exact, but it's pretty close to 50. Wood meter sticks are not homogeneous, so they are likely to vary around. But for simplicity, to make sure that we understand the core concepts here, I don't want to get too bogged down in all the details. So there's a couple of assumptions we'll make, I'll mention along the way. And you can include those when you think about your percent errors and your conclusion statements. So I need to, before I start putting all these things on here, the reason I mentioned the forces is because I need the mass of the meter stick. So I'm just going to lay it here on this and make sure it doesn't lay on anything else. And I see we're at 96.8 grams. So I'm going to put, this is the meter stick. Mass is 96.8 grams. Okay, I'll let you convert that to kilograms later for your calculations. All right, so now this is going to be a little difficult because I'm doing all this by myself, videoing and the lab itself. So I'll try not to stand in the way of the camera, but I'm going to try to place these on. Now the first thing I'm going to do to make it easier to hang masses on this guy is I'm going to put two rubber bands on. That should be good. Then we have these clips, okay? These little clips I'm going to slide on, and they have strings attached to them. Okay, these strings are going to be threaded over the pulleys, all right? So I'm going to have some masses that we'll place on there. So that's going to be a little bit of a trick. I'm going to go ahead and pick maybe, I think maybe I'll try a 50-gram mass, and I suppose we can do 100 on here. Okay, here comes the tricky part, and that's going to be hang these over. Through here. Try to hold this up. So this is definitely not easy to do by yourself. One string is a little longer than the other as well. So I'm not actually running them over the pulley at the moment. I'm just letting them hang there so I get a little bit of friction to assist me. Hang the mass hangers on. Okay. I'm sure this makes for exciting watching. I'm going to let that rest if I can. Let that rest on there. Okay. Now, of course, when I release it, it's pulling up here, which means I need more force acting down on this. So I'm going to go ahead and just try a mass on here and see what that does. Still not enough. Possibly too much. Okay, so getting close. And pretty good there. All right, so now on the other side, I definitely need some more mass to pull this up. And then we'll start working on fine-tuning this. Not bad. Okay, so at this point, we notice that it's rotating like this. Now, as far as our axis of rotation, because it's in equilibrium, we're going to be able to pick what that axis is going to be. So it could be at 50, it could be at the end. We'll do both of those later as we talk about it. But what I notice is that I've got I need probably just a little bit more force to lift this side, right? So if I slide this down, at that point, what I just did was I changed the angle. Okay, so you notice that if this is further out this way, the angle is larger, I will have less component, more component in this case. So if I slide this over, I need just a little less in the vertical. So this is much easier than me trying to change the masses around. Okay, so now that is pretty good. Okay, so ideally, these things would be placed at the ceiling, right? So that these would go very far, so that any small changes here would not make massive changes to my angle. Because if I make changes to my angle, that's going to change everything that I have going on here. It's pretty level, not bad, maybe slightly off, but I think we'll take that. Okay, so a couple of things I'm going to need to do is I'm going to need to make note of what my forces are, okay? We already know what the mass of the meter stick is. We found that, so you'll be able to calculate the force to the mass of the meter stick. Then I'll give you what these masses are as well as the ones on the ends over here, okay? And then finally, we also need to measure what the angles are, okay? So let's go ahead and make note of the forces. Now, looking at the book, they have these listed a little bit differently than the way I have them on here, okay? So they're showing F1 as being a force down, they're showing F3 as being the weight of the meter stick, and F4 as being this mass pointed down. Then they're showing F2 as being up and to the left, and they're showing F5 as being off in this direction, okay? So I'm going to write them down in that way so it'll be a little easier for you. However, I don't suggest that you necessarily just blindly follow along. Say equation 8.3a or 8.3b. They can be a little helpful, but they can also be very, very confusing because if you try to just simply plug this in, you won't know what you're doing. But if you'll think about what I'm going to say here in just a moment to make this much, much easier. All right, so I'm going to write down force 1, force 2, 3, 4, and 5. And again, I'll share these with you later. All right, so force 1, they are calling the guy that's hanging over here. This is a 100-gram mass, okay? So that's going to be 0.1 kilograms, okay, times G. All right, then force 2, they're showing as the one that's off in this direction, okay? Now, this does have an angle associated with it, so we'll measure that angle here shortly, and I'll make note of that off to the side, okay? But I've got two 20-gram masses here on top. I have a 100, so that's 140 plus the 50 that's down here, so it's 190 gram total, because the hanger is 50 grams. So it's 190 grams. And of course the force would be multiplied by G. Now F3 is the weight of the meter stick. So we've already done that earlier. And that is going to be 0.0968 kilograms times G. Okay, I told you I was going to let you do that. Now I've done it for you. You can thank me later. F4. The one over here, okay, this is a 50-gram mass, so that is 0.050 kilograms times G as well. And finally, F5 is the one off over here. That's going to be a 100, I believe, plus 10 plus 50, so it's 160 times G, okay? So now we need to make note of the angles, and at that point, I'll tell you kind of how we're going to go about making the calculations, and we'll be done. The rest will be up to you, okay? So looking at the angles here, there's a couple ways we can do it, all right? They give you graph paper in the lab manual, and they talk about measuring the height and measuring the triangle itself, drawing it out on the paper. You could also try to do, there's a few different methods you could try to do this, but there's one major problem with doing the triangle method if you tried to go all the way up to a point up here, because this is rounded. You don't know where the point really is. So one way you can handle that would be to make a mark here somewhere and then measure the distance from here back to the meter stick, and you can measure the distance down here, or you could measure from where this makes its contact point out to here and then up at that point. That might be the easiest way to do this. Another way would be to take a protractor like this and measure. That can be a little difficult because you're having to put pressure down here on this, and it's hard to get it lined up. But that is kind of a nice way to do it at some point too. I'm going to go ahead and do the front. So I'm going to come around and kind of block the camera just a little bit and find this angle, okay? And let's make sure I need just a little more. There we go. Okay, so I just made a slight adjustment here. What I'm really doing is getting this to rotate that way so that it levels it out just a little bit better. Okay, so what I'm going to do is I'm going to just come out, let's say from this marking right here of wherever this is placed, out to, let's just pick the 30 centimeter mark. Okay, so if I do that, I will know that I'm at, this will be what, 37.7. So that's 7.7 centimeters that I'll be along the base of my triangle. Okay, so I'm going to try to mimic this and draw it. This was for, let's see, F2, I believe. Yes. So for F2, I'll put theta here. So for F2, we're going to have something that looks like this. That is 7.7 centimeters. And then for the other side, I'm going to measure from 30, as vertical as I can go. So that would be about 10.5. Okay, so 10.5 centimeters for the height of the triangle, and then I had the base as being 7.7 centimeters. From that point, you would be able to apply the tangent, inverse of that to get your angle. Okay, so that's for F2. Let's go ahead and apply the same idea over here for F5. And make a little sketch there for me. And so I'm just going to pick some round value. So that would be from maybe the 70 mark over here. And I am at about, let's see, that's 61.9. So it's right at 62. So that'd be 8.1. So 8.1 centimeters for my base. And let's measure from 70 up to where this crosses, assuming I can keep this. So what I'm using is I'm using the lines here as a vertical to help me keep this line so that it is perpendicular, and this becomes an accurate measurement. That's going to be about 8.1. 8.1 for the height there. Wow, so that's going to be 4 45 degrees. All right, and which one way we also do that is we could line this up. It's a little bit hard to do, but I can see there that, yep, that would work out to be about 45, so interesting. All right, so makes that kind of nice. So now we have both F2 and F5 ways to calculate the angle. All right, now here's what you have to do. Okay, looking at the lab manual, they ask you to determine forces on the meter stick. Then we want to look at the horizontal and vertical components. Okay, once you know what the angle is, okay, or however you want to apply the geometry that I'm giving you here, that I'll give you a copy of what I've written down. So however you want to apply that, you will then be able to calculate both the horizontal and the vertical components. Okay, so I've given you the masses, you know what G is, and now you have the information in order to find the angle so that you can find the horizontal and the vertical components of these two forces. You know the mass of the meter stick, you know these two masses here. So here's what they're going to ask you to do. Okay, they're going to ask you to first verify that the forces all sum to be 0. Specifically, I think they're going to ask you to find the percent deviation. Yes. Okay, so we're going to find the percent deviation of the upward forces versus the downward forces. Okay, so let's do that for the y-axis first. So the very first step is to compare forces. So take these two components, add them together. Take this, and the weight of the meter stick, add those together. Remember, we're doing the weights here, so for the forces. So you've got 1, 2, 3 that are down, the two components here, up. You take these two, add them together, compared to these three added together, and look at the percent deviation between those. Another way to do it would be to see if they all add up to be 0 if you let, say, up be positive and down be negative, or whatever you choose there. Okay, next thing you need to do is compare the horizontal components. So in other words, look at this component here and this component and see if they're equal. Okay, so you'll compare those two to one another. All right, so after we've done that, we're now going to go to the torque idea. So if you'll remember, we're going to assume that the center of mass is at 50, okay? So that's going to have an effect. There's one more bit of data I need to write down over here for you, and that's going to be the location on the meter stick. And you're going to be very careful about this. Don't just blindly plug these numbers in. You will for one part, but for the second part, you're going to make a change, okay? So what they're going to ask you to do is they're going to say, calculate the torques for each of these 5 forces, assuming that, look and see which side here this is printed on. All right, so they have 0 over on this end, okay? So if we were to assume that our axis of rotation, remember it's not rotating, so we're free to pick whatever point we want as an axis of rotation. You could do this actually even if it was rotating, but as long as we're consistent, we'll apply those torques. Now what's going to change about each torque is going to be where it is located relative to the axis that we choose. So if we choose 0, which that's what they suggest for the first one, in other words, this end of the meter stick, then that means that this component of the force, if I was holding it here, this component would act upward, trying to rotate it in this direction, okay? So if you're looking at it there, that would be a counterclockwise direction, okay? And it turns out to be positive, but you'll talk more about that in the lectures at some point. Okay, then if I were to go down and look at this force, this component here, which I think we called F5, this vertical component of F5 is the one that would also cause a rotation in this direction, okay? Now, the only other thing to talk about is the two horizontal ones, for at least from the upper side up here, the horizontal components, but those are horizontal, meaning they're parallel to this. So just like with the door earlier, you are not going to be able to cause a rotation by applying a force only parallel, right? So if you were to plug that in blindly into the mathematical equations, they would turn out to be 0 for torque, right? So your FR sine of theta. But we don't need to worry about those horizontal forces because they're not going to contribute to any rotation, okay? And all we're comparing here for this second step is we're going to sum up all the torques and see if they're equal to 0 is basically what we're doing, okay? So another way to think about that is, if I'm holding it here, this torque and this torque are both acting to operate to rotate it in this direction, okay? The torque due to this guy, the torque due to the weight of the meter stick, and the torque due to this are all three pulling in this direction, trying to cause it to go clockwise, okay? So then that clockwise direction then would be a negative torque, and then you would have the two positive torques, and you could sum those up to equal to 0, or what they suggest you do here is find this torque, this torque, this torque, this torque, this torque, add these two together, add these three together, and see what the percent deviation is between that set if you're allowing this to be 0, okay? Then they're going to ask you to repeat the same process, except you're going to let the center of mass be your axis of rotation. If I do that, that's going to change how many torques I actually have contributing, okay? So think back to the door. If I had a door and I was trying to open the door like so, if I come over and apply a force at the hinge of the door, in other words, push the hinge, I'll never open the door, right? So the only way I can get a torque is if I increase my R out to some non-zero value. In other words, try to pull the door open from somewhere other than the hinge, right? So the further you get away from the hinge, the easier that door feels to open. All right, so what you would then do is if you're holding it at 0, notice, let me actually hold it at 0 first, okay? I'm going to let go and watch what happens. It rotates down. Why? Because of the force of gravity acting on the mass of the meter stick here. So we have the torque due to the mass of the meter stick, okay? There's force due to gravity on the meter stick that causes it to rotate in this direction. So that's what we saw a moment ago, okay? This would do the same thing, this would do the same thing. So all three of these combined are trying to rotate it in this direction. Whereas this piece and this piece combined, the torques are operating in this direction. All right, if I hold it instead of here, if I hold it at the center of mass, and now I let go, it doesn't rotate. That's the same thing as pushing on the hinge. In other words, if the interesting thing about mass is that when you calculate force due to gravity, you can calculate it based on where the center of mass is located. And you don't have to worry, in that case, about how it's distributed. There are other things where it does matter, but in this case, it's very nice and easy. We can simply just treat it like all of the mass of the meter stick is acting right here at the center, and you'll get the correct result. So if I hold it here at the center, it never rotates, right? So in other words, the torque due to the mass of the meter stick, the gravity acting on the mass of the meter stick, that torque would be 0, because R would be 0 for that, all right? Then this guy would be pointing in this direction. It would try to rotate like this, okay? Whereas this one would try to rotate like that, right? This force is going to try to do this. This force is going to try to do that. So in other words, the torque due to this, the torque due to this are both acting together. This torque are both acting together. So you take these two torques, add them together. These two torques, add them together, and compare those two sets of numbers, okay, by percent deviation. All right, last thing I'm going to point out here is I'm going to make notes of the R values, just so that you know. Remember that the mass of the meter stick, we are going to assume that it is at 50 centimeters, okay? So I'm not going to write that down. That should be pretty evident. But if I come over and measure to see where F1 is going to be at 39.6. It's kind of in between, so there's a little bit, there's about a ½ centimeter worth of error in that measurement. All right, so make sure I'm writing down the right ones. Yeah, F1's the one they have down. So for F1, I'm going to put X here, not R, because your R value is different, okay? So this is X as in position on the meter stick, all right? So we have F1, F2. Okay, I am going to include the F3 on here, but all right, so F1 is, when I come over to read where that is, again, because I've already forgotten, it was 37, oh, I'm sorry, F1, it was over here, 39.6. Okay, F2 is going to be this guy going up here. That's at 37.7. Okay, F3 is the meter stick itself, and of course we're going to assume that to be 50 centimeters. Could be off by a little bit there, maybe even as much as 4 millimeters or so. All right, so just based on what I measured earlier, or looked at earlier, but that's okay. We're going to make that one small assumption. F4 is going to be this guy hanging down. Let's see where he is. And that one is at 59.7, I think is going to be about right, 59.7. And then finally, we've got 61.9. 61.9. Okay, so the positions that we have here, here's how you're going to calculate the torques. You're going to take the force, let's say for this guy here, you're going to take whatever, it's the 100 gram mass, I believe, yep. The 100 gram mass at whatever I said the position was, 39.6 centimeters. Well, when you hold it here, you would multiply by 0.396 meters, right? Because that is the distance from the axis of rotation. But when you go to the second part of the torque, so in other words, I guess it would be the kind of the third thing you have to calculate. If I held it at 50 centimeters, then the distance is now going to be 50 minus whatever this value was. So in other words, it's going to be about 10.3, something like that. Is what 10.4, about 10.4 centimeters away. Okay, so 0.104 multiplied by 100 when you're doing it based on the zero or the axis of rotation being at the 50 centimeter mark. Okay, so keep that in mind that when you go to calculate these things, the forces are easy. These two add together. This one, weight of the meter stick, add together, see if they're equal. Check the horizontal ones as well. When you go to torque, horizontal forces don't matter for torque, so we don't worry about the horizontal components of these forces here. We only care about the vertical. It's just the perpendicular that's going to play a role. And you'll start by holding it here. You'll take the distance from here to where this is, so in other words, that mark that I wrote down. So it'll be that force component multiplied by this distance. Then you'll have this force multiplied by this distance, and the meter stick itself, of course, is at 50, and the mass at the weight of the meter stick. Then you'll take this weight, multiply by that distance, and of course this one multiply by that distance. So then you'll look at these two torques adding together, and those three torques adding together, and you'll see how those compare to each other. Should be equal, depending on how good a job I did here. All right, so then of course we'll go to the 50, and then what's going to change there is the forces are still the same, but the R values change, okay? So assuming I'm grabbing this here at 50, a little hard to see, but yeah, it was close. So if I were to hold it here at 50, the distance from here to here would be R now instead of the distance from here to here, because I'm holding at this point. So I have this distance, that, and of course the mass of the meter stick would have a distance of 0, therefore its torque contribution would be 0. Okay? All right, so that should do it. I'll provide this bit of information to you on Canvas, and you can calculate everything that you need to here and do the write-ups best you can. It's going to be a little awkward. We'll do the best we can with this. And then, of course, contact your TAs if you have any questions or need a little bit of clarification. Okay? Thanks. Good luck.